Hello everyone. In today's lecture, we are going to study how to obtain particular integral of the given non-homogeneous differential equation, and in that way we are going to obtain the general solution to the given non-homogeneous differential equation. So let us see what are the different methods to find particular integral. There are total three methods to find particular integral, which are: first one is general method, second one is shortcut method, and third one is variation of parameter method. What is the particular integral? For the given differential equation, non-homogeneous differential equation, phi of d of y equal to f of x. If we operate the operator 1 upon phi of d on both the sides, then on the left hand side we will left with y, which is the particular integral, and on the right hand side we will be getting 1 upon phi of d of f of x. So particular integral is equal to 1 upon phi of d of f of x. This is general formula for particular integral. Now using this, we will obtain particular integral to the given non-homogeneous differential equation. We will see first method, which is general method. Now let us go to that method. General method. For the general method, we will consider first case with one single root as d minus a into y is equal to f of x. Suppose this is the given differential equation, non-homogeneous differential equation, which is having only one factor d minus a. So this is the first order, first degree differential, linear differential equation. In this case, how we are obtaining the solution? We are obtaining the integrating factor. So that integrating factor will be what? It is e raised to minus ax. Everyone knows how to solve linear differential equation of first order and first degree. Once we get the integrating factor, then the general solution to this differential equation is given by y into integrating factor, which is e raised to minus x, is equal to integrating factor into the right hand side function into which is f of x into dx. Here we are not going to add the arbitrary constant, as already we are considering arbitrary constant into the complementary function. What happens if we add here arbitrary constant? If we add arbitrary constant, finally it will get added into the complementary function only. So it is not making any change in the solution. So therefore we are not going to consider integrating constant in this expression, and therefore further simplify it. So take this e raised to minus x on the right hand side. So therefore we will be getting y as e raised to x into integration e raised to minus x into f of x dx. Now see, if we operate the operator 1 upon d minus a on both the sides, we will left with y on the left hand side, and on the right hand side we will left with 1 upon d minus a of f of x, which is the particular integral. So y is equal to pi is equal to 1 upon d minus a of f of x is equal to e raised to x integration e raised to minus x f of x dx. So this is the formula, or which is the general method to obtain the particular integral for the given differential equation. We have considered this case because for non-homogeneous differential equation, we are always going to factorize that phi of d into the linear factors, and that's why here we have considered case with only one linear factor, and we can extend that case to the number of linear factors. So here we have considered the linear factor as d minus a. Now consider the next case. Consider the next case, which is d plus a into y is equal to f of x. Again, it is a linear differential equation in y. So obtain the integrating factor, which is e raised to ax, and its solution will be y into e raised to x is equal to integration e raised to x into f of x into dx. Again, here we haven't added the integrating constant. Now multiply on both sides by e raised to minus ax. So that will gives us y is equal to e raised to minus x integration e raised to x into f of x dx, which is the particular integral for the given differential equation, and therefore particular integral is equal to 1 upon d plus a of f of x is equal to e raised to minus x integration of e raised to x into f of x dx. Now in the previous case, put a is equal to 0. Any one of the two previous cases, put a equal to 0. So that will gives us pi, particular integral, is equal to 1 upon d into f of x, which is equal to, so when we replace a by 0, e raised to 0 is 1, integration e raised to 0 is 1 f of x dx. So this 1 upon d, it is nothing but antiderivative operator, that is integration. So 1 upon d of f of x is equal to integration f of x dx. Next, we will consider as the particular integral equal to 1 upon d square into f of x. So which is equal to, we can write it as 1 upon d into 1 upon d in of f of x. So means we are going to operate the operator 1 upon d twice on the f of x. So first time when we operate, then we will evaluate the integration of f of x dx. Follow this color code. Evaluate that integration, suppose it will be gx, then evaluate the integration of gx with respect to dx. So that will gives us the particular integral 1 upon d square of f of x. In same way, particular integral 1 upon d cube of f of x, means we have to integrate this f of x 3 times like this. So clearly, if we follow this color code, we will be easily evaluate this particular integral. Now we are going to consider last case in general method. Suppose our non-homogeneous differential equation is of the type d minus a into d minus b of y is equal to f of x. Obviously here I have considered the left hand side already expressed into the linear factors. So therefore the particular integral will be given by y is equal to 1 upon, means on both the sides we are going to operate the operator 1 upon d minus a into d minus b. So that will gives us particular integral as 1 upon d minus a into d minus b of f of x. Please keep in mind that this d minus a into d minus b is our phi of d, and if you recall the formula for particular integral, we have been written it as 1 upon phi of d of f of x. Now here one way is we have to operate this operator one by one on the f of x. Okay, so we will see that first. So 1 upon d minus a into 1 upon d minus b of f of x. So first we are going to operate d minus b on the f of x. Now using first case, we will be getting it as 1 upon d minus a into e raised to bx integration e raised to minus bx of into f of x dx. We simplify this term and we will call it as g of x. Okay, because after simplifying we will be getting it as function of x only. So we will call it as g of x. So we left with 1 upon d minus a of g of x. Again use the first case. So that will give us e raised to x into integration of e raised to minus ax gx dx, g of x into dx. So see, in this way, whenever the product of linear factors is there, then we are going to operate it one by one on the given function f of x, and in this way we can evaluate the particular integral. So it is up to us whether to operate 1 upon d minus b first on the f of x, or to operate the 1 upon d minus a first on the f of x, depending upon what is the f of x is given. Or this is the one way, or what is the second way? So let us go to the second way. This particular integral 1 upon d minus a into d minus b of f of x, what we can do here, we can obtain the partial fractions. Okay, for this which can be obtained as 1 upon a minus b into 1 upon d minus a minus 1 upon d minus b of f of x. So these are the partial fractions for the given term 1 upon d minus a into d minus b. Now operate this operator on the f of x simultaneously like this. So 1 upon a minus b into 1 upon d minus a of f of x minus 1 upon d minus b of f of x. Again, using the first case, we can simplify this and we will be getting the particular integral as 1 upon a minus b into e raised to x integration e raised to minus ax f of x dx minus e raised to bx into integration e raised to minus bx f of x dx. So simplifying this, we will be getting our particular integral to the given differential equation. So in this way, we can evaluate particular integral in the using general method. I hope you have understood this. Thanks for watching this video. For next method, uh, in the next lecture, we are going to solve examples on the general method. So keep watching. Thank you.